welcome back to our class. So at the beginning, I have two announcements. So basically, for the assignment 4, I think we actually, the deadline is actually going to do in 1 week. Please keep in mind that the deadline is very important, and you do not want to miss the deadline. And also, on the other hand, for assignment 2, the TA has finished grading the assignments, and the corresponding grades has been returned by email. So please check your email for your results for assignment 2 here. Okay, so today we are going to continue to talk about a network of flow algorithm. So at the very beginning, we will briefly talk about, further algorithmic improvements. I think the main part of today, we will talk about some applications of network flow algorithm that includes a bipartite matching, disjoint path, circulation with demands, and also a survey design. So depending on whether we have time, I think basically for the next about 2 lectures, we are actually going to introduce, because this class is called algorithm analysis and complexity theory, but we have been talking about algorithm design for all of the time. I think basically, for the next few lectures, we actually talk about some harness result. Basically, we want to talk about NP and computational intractability. I think we have a chance to begin a little bit today. Let's see actually the progress that we made, and that probably depends on that. Okay, so let's get started. Okay, so today we are actually going to continue to talk about the network of flow algorithms. So basically, last time we gave a very detailed introduction to this algorithm, the Ford-Fulkerson algorithm. And actually, the Ford-Fulkerson algorithm can output the value of a max flow or the mean cut problem, which are actually equivalent, and actually can output the solve the problem in time O of m times c here. And secondly, after running the Ford-Fulkerson algorithm, it actually can give some mean cut. Basically, the Ford-Fulkerson algorithm is an algorithm for solving the max flow problem. But actually, we know that the value of the max flow and the mean cut, they are equal. And actually, after running the Ford-Fulkerson algorithm, it also gives a mean cut in O of m additional time. It's just like in the previous proof, we just ran the Ford-Fulkerson algorithm and use a BFS or DFS to determine basically the set that is actually connected that is reachable from the starting point S, and actually that is going to give you a mean cut here. So the third point, actually, we will use it a few times today, is called the integrality theorem. That actually there exists a max flow such that, as long as all of your weights basically this capacity constraints they are integers. So as long as everything here is an integer, basically we can prove that actually the output of the max flow, basically the value that we achieve here, is actually also an integer here. Okay, so any questions for the last lecture? Okay, so here I think the first topic today is that we want to very briefly talk about the improvements upon the Ford-Fulkerson algorithm. So the Ford-Fulkerson algorithm has been there for approximately like 60 years. And actually, you can imagine, as we discussed today, that the network flow algorithm, they are very important. Basically, the max flow problem, the mean cut problem, these problems per se, they already are very important problems. But also on the other hand, it actually has a lot of applications. So like a very naive understanding of this, that actually for the Ford-Fulkerson algorithm can give us a time complexity O of m times c. But it's a very natural question to ask whether actually we can improve the time complexity of the max flow problem or the mean cut problem. So I guess this is going to be a little bit evolved, as you can imagine. Basically for improving the time complexity, there are a lot of later sophisticated works that actually study this. So I guess we probably cannot cover a lot of details, but I guess at least let's very briefly mention some of the intuition here. So actually, speaking of the Ford-Fulkerson algorithm, you can imagine that actually one of the main bottlenecks is that basically we have this value C here, which is actually a capacity constraint, and basically we have the M to be the number of edges here. So each time when we run the Ford-Fulkerson algorithm, we run this idea of augmentation, and basically the only promise that we can have for the augmentation is that the value, given all the basically all the capacities are integers, each time it increases by at least 1. But this is probably a little bit slow and actually a very important intuition here. Excuse me. So a very important intuition here is actually we want to think about closely about this, whether each time we can improve further. Basically improve by 1, and probably we are not satisfied with that. And actually maybe we want to choose a little bit a larger value. So in particular, maybe we want to choose truth path. If that's possible, maybe we want to choose the path with the highest bottleneck. Capacity increases. Flow. Actually, this is going to increase the value of the flow by a maximum possible amount. Okay, so I guess this is quite intuitive because if you just arbitrarily run the augmentation each time, you're only getting the guarantee that you at least increase the value by one. But actually, in general, we want to target for a larger increase along this. So the general idea here is called oh, excuse me. So the general idea here is called the capacity scaling. So what do I mean by that? So in general, maybe we want to think about, we don't want to increase the value by one, we want to increase it by a little bit larger value. So the thing that we actually do here is that maybe, for instance, let's suppose that for instance, because we have this value C, like the capacity constraint on the vertex S here that when we discussed last time. So maybe, for instance, we can assume that C is actually larger than or equal to 2 to the K, but smaller than 2 to the K plus 1 here. So basically, a very important thing that we will do is actually we want to maintain a scaling factor. We want to maintain a scaling factor. Let's denote it by delta, which is actually initialized as to the K plus 1. So we don't need to initialize a large delta here because we basically know what is the range of the C here. So that is basically something suggesting us, and actually at the beginning we have a scaling factor, a delta that is roughly speaking approximately the same as the value C here. And basically a very important observation that we are going to do is that we are actually going to let a graph. Recall that this GF is the residual graph that we talked about last time, and actually we gave a very heavy introduction for this graph GF here. So basically we denote GF with the parameter delta to be the subgraph of the residual graph. But actually it only consists of edges with capacity larger than delta. So the thing that we do is that actually instead of considering like augmenting path on the original graph of GF, on the original residual graph GF here, we actually consider, we have the scaling factor, and actually we surfaces that we consider, in some sort of like heavy edges. That basically edges has a corresponding capacity, at least delta here. So basically we only consider the subgraph of the original graph, and actually we find the augmenting paths on this GF delta here. And actually until there is no. And actually, because for this graph GF delta, we actually deleted some of the edges where the corresponding weight is small. It can definitely be the case, and there are actually augmenting paths in the original residual graph GF, but after you consider the GF delta here, after you omitted some edges here, actually it does not have further augmentation paths anymore. But in that case, we know it is the situation that we are going to further shrink the scaling factor here. So we clearly see that the intuition is that at the beginning, we have a large delta here. And in general, as long as we can do the augmentation, it is very good because actually, because you are considering the graph with capacity, each edge with capacity at least larger than delta. Each time you can do the augmentation, you actually increase the value of the flow by delta here. And if you cannot further increase, you just shrink this by half, and you just do this further again. So this idea of a capacity scaling is actually very intuitive, but unfortunately, due to the time limitation, I guess I probably won't have time to actually further introduce the details. But basically, I can make a very brief summary about what we can actually achieve using this kind of a capacity scaling idea. That basically we can prove that actually, of course, it is quite trivial that using this kind of idea, we have at most O of log C scaling phases. and actually O of M augmentation per scaling phase. So by a scaling phase, it just means that we have not reached this part where we make this delta smaller. And actually, for each fixed delta here, we are actually going to run O of M corresponding augmentations. And in total, of course, because we are actually starting from delta to be 2 to the k plus 1 until delta equals to 1. And actually, when delta equals to 1, of course, here, I mean, according to this definition, I mean, GF, we just like note. Actually, a GF1 just equals to GF. Because, I mean, for all the edges in the residual graph, I mean, as long as it has positive weight, this weight should be at least 1 because we assume that all the weights are integers. So basically, of course, GF of 1 equals to GF. But at the beginning, this delta is large, and we keep shrinking this to the value. I mean, each time we cannot find like a further augmentation path, we just make this smaller to be a delta over 2 here. In total, I guess this algorithm, it is intuitive to say that basically this algorithm has O of log C scaling phases, and you can actually prove that O of M augmentation per scaling phase that actually holds in this this idea plus actually under this for the Fulkerson algorithm. And actually this implies that in total we have O of M log C augmentations in total. And basically, as we described last time, I mean, each time we do the augmentation, the cost is O of M here. So that is basically suggesting that the overall cost is O of M squared log C cost. So if you're interested, I guess this is actually introduced in our textbook. So if you're interested in more details, you can actually check section 7.3 of the Kleinberg-Tadeusz book. Okay, so basically compared to the original result due to for the Fulkerson, in other words, max flow and mean cut can actually be solved in this complexity, which is O of the minimum of MC and actually M squared log C. Okay. So this is basically a very brief discussion about how we can actually further improve the Fulkerson algorithm. So it depends on what we call like a further improvement. I mean, this idea based on capacity scaling, because actually the number of augmentations in each scaling phase is actually, we can prove that this is O of M. I mean, in some cases, I mean, if you look at this minimum here, so if the M here is actually much larger than N here, or maybe after using the capacity scaling, you are even not as good as the original algorithm. But the key point is that, so recall that we also introduced some other problems. For instance, in dynamic programs, we actually introduced the knapsack problem. In the knapsack problem, basically we have this W to be the weight of the corresponding knapsack problem. And actually in that case, we give an algorithm with cost O of NW. But actually, until now, I think as far as people know, people don't know how to give like a polylog algorithm that is polynomial in the log of W. Basically, this algorithm with this cost. This is still widely open in the classical literature. So basically, in terms of algorithm design, I think we briefly mentioned that we want to have like strong polynomial time algorithm. Then in general, because for instance, as long as you have n inputs, I mean, basically n inputs about the knapsack problem. In general, you don't want to have your algorithm to be case dependent. That basically, if your weight, the weight here is huge, then your algorithm is actually going to be slow here. In general, we want to have a fast algorithm that hopefully does not depend too much on the instance. So here, I mean, the thing that we want to pursue here is basically the same for the Fulkerson algorithm. I mean, in general, actually, for the Fulkerson algorithm, for a lot of applications, I think, for instance, the applications that we are going to introduce today, basically the cost of O of MC is actually good enough. But actually, people are in general interested in this algorithm design. The direction is that people hopefully we have like a smaller dependence in terms of C here. Especially we want to have like a polylogarithmic dependence in terms of C here. And actually, you see that there is basically a difference between the max flow problem and the knapsack problem, where actually there exists. At least polynomial time. Strong polynomial time algorithms for the. Sorry, I probably shouldn't say a strong polynomial time, but actually a weak polynomial time algorithm. That in general, at least we can reach a polylog C dependence here. Although we cannot totally get rid of the C dependence here. I think as far as I know, I don't know an algorithm that does not have like a dependency in C to solve the max flow problem. At least here is actually an algorithm with cost polylog in terms of C. So this is basically something quite good. Okay, so this is a very brief introduction about what is best that we can achieve using basically the idea based on the focus on algorithm. But in general, when design algorithm, there are actually a lot of advanced research. People really, due to the importance of the max flow and min cut problem, people have been really working very hard on this. And I think it is very important that in general, people want to have a good algorithm for solving the max flow and the min cut problem. So I guess let me actually also very briefly mention about like the state of the art result here. So how about like the best known result? So this is actually some direction. Especially algorithm for the max flow min cut. People are really working very hard along this. And actually, I am happy to announce that actually just this year, 2022, there is actually a breakthrough result along this. So actually, currently, state of the art result. It's basically achieved by actually quite a few authors, Chen, Gutenberg, and Sekdeva. So the title of this paper is actually quite intuitive. So the title of the paper is called the maximum flow. And they study another very related problem called the minimum cost flow in almost linear time. So this was actually a Fox 2022 paper. So Fox is basically one of the best conference in theoretical computer science. And actually, if you're interested, there is also an archive number here. So this is a super long paper, by the way. I think it's probably more than 100 pages. I guess this is probably in general of theoretical values, but I guess in terms of theoretical values, it is a very important result because it is basically the first result that can show almost a linear dependence in terms of M, while we can keep the polylog dependence. So the complexity is basically M to the 1 plus small o1. Let me introduce what small o1 is in a minute. So we're actually the U here. The U here is actually an upper bound. The capacity of each edge. So because the C dependent, the C, the parameter C here is actually defined in terms of the total capacity in S here. So basically it is not very difficult to see that actually C is smaller than N times U. Because actually looking at S here, and actually S can have edges to at most N vertices, plus the total number of vertices at most N here. So clearly we can see that C is actually smaller than N times U here. So basically, they prove that their algorithm has complexity on big O of m to the 1 plus small o1 times log U here. So the small o1 here, actually, basically in the when we at the very beginning of the class, we introduced this big O notation, and they're actually a small O notation. Basically, this represents a value. In terms of, because we're talking about a function in terms of m here. So we just say that this represents a value of m such that the limitation of m goes to infinity fm over m equals 2. So basically, this is something that is strictly dominated by basically when m goes to infinity, this is going to be very close to 0. Well, actually, I think I probably basically I think I should probably write 1 plus O1 here. Because basically I'm talking about, sorry, I guess this is a little bit messy here. Maybe let me write like this. I think I wrote an extra over m here in my lecture preparation. But what actually it means, well, this small O1, that just means that, I mean, in terms of m here, this is really going to 0 when actually m goes to 0. That is, but here actually in the exponent. Okay, so I guess this probably finishes the discussion about, I mean, further improvement upon like Ferguson algorithm. In general, you can clearly see that actually the Ferguson algorithm is pretty good. That actually the complexity is O of m times c here. Actually, for a lot of applications, we don't care that much about like whether this is like a c here or like a polylog c here. Actually, typically for a lot of cases, c here is not that large. I mean, in terms of the max float. But the point is that there are some like further directions to further improve. I mean, the Ford-Ferguson algorithm, especially this capacity scaling, is a very direct improvement upon the Ford-Ferguson algorithm. It's just like maybe we can we don't maybe we don't directly improve we don't directly use augmentation idea, but actually we can consider like another parameter delta here that hopefully, I mean, each time we augment along only along like very heavy edges with a large capacity. And basically using the augmentation idea, we can already give an algorithm with complexity like m squared times log c here. Actually, there are some like later further improvements, and there are like very sophisticated work very recently that can improve, I mean, the m dependence from m squared to something like m to the 1 plus small o1 here. This is actually going to be a much smaller, and in terms of the c dependent, it's still going to be a log c here, basically. Okay, any questions about like these discussions about like further improvements upon the focus? So if there is no question, I guess, I mean, this is probably, I mean, what I was saying is probably the radical part, but I think here, I mean, in general, I mean, we want to introduce algorithm for interesting problems. So let's see some interesting problem about like the using the network flow algorithm that actually maybe we want to initiate from graph, but actually we can see that the applications of the network flow problems can even go out of graph problems. Okay, so the first problem that we are actually going to introduce is a problem called the bipartite matching. So recall that in our actually in our first lecture. So basically we introduced this problem called a stable matching. So here we actually are going to introduce a related problem, as suggested by the name. It's another matching problem. But here the problem that we are actually going to take a look is the bipartite matching. It is actually a closely related problem. Another common matching problem. So actually, how is this defined? So because talking about, I mean, matching. So here, I mean, the convenient way is still to describe this using a graphs. So here we say that the input we have is basically an undirected bipartite. Which is actually a G equals to L union with R with the edge set to be E here. So here we say that basically a matching. A matching is actually a subset of the edges. So we say that M is actually a matching. If each node appears Yeah, at most one edge. And the goal here is to find a maximum matching here. So formally speaking, I want to find a matching with maximum cardinality. Okay, so maybe let's see a quick example here. So for instance, because we are talking about a bipartite graph, so we are definitely going to draw two parts. So one part represents L and the other represents R here. So let's assume that, for instance, maybe you have a graph where both left and right you have capacity 5. And basically, maybe for the right-hand side, let's say mark them as A, B, C, D, and E here. Okay, so maybe let's, for instance, consider this graph. So let's say we have this edge, say we have this edge. Maybe let's say we have this edge. Okay, so this is actually a bipartite graph because we can regard the left, I mean the vertices 1, 2, 3, 4, 5 as the L part, and the right-hand side part, A, B, C, D, and E, they represents the R, the right-hand side. So what is the value of the bipartite matching problem? So basically, we are actually supposed to find a matching with a maximum cardinality. So let's actually take a close look at this corresponding graph. So there are actually, different ways that we can find matchings in this graph. Let's actually copy and paste a few instances here. So let's, for instance, maybe we can take a look at this. For instance, assume that maybe we take 1 with B here. So here, keep in mind, a very important restriction of the bipartite matching problem is that actually each node should appear in at most one edge in M here. So basically, after we choose the edge on 1 and B here, we are not supposed to choose, any edge corresponds to 1 and B anymore. So we are actually going supposed to choose some other edges here. So here for the vertex 2 here, the vertex 2 here only has one edge to B here. But actually, unfortunately, B has been chosen. So it just means that we cannot actually further choose any edges from 2 here. But actually, we can choose some further edges for the vertex 3 here. So for 3 here, maybe let's, for instance, choose the edge 3A here. And maybe, for instance, for 4 here, we can choose the edge 4E. So this is actually just going to give you a matching composed of the edges 1 B, 3 A, E here. But there are actually some other choices that we can make. So basically, in our discussion just now, one thing that we got a little bit noticed is that basically when we do the vertex 2 here, the only possible edge that we can choose for the vertex 2 here is that basically the edge 2B here. So maybe, hopefully if you want to find like a larger matching here, maybe we want to choose this vertex 2 here. So maybe let's, for instance, then we are probably going to choose this edge. If we choose this edge, if we then look at the vertex 1 here, the vertex 1 is only adjacent to vertex A and B here. The vertex B has already been selected. So basically, we need to select this edge. And similarly, based on further observations, so actually, for instance, maybe we can look at the vertex 3 here and basically 4 here. So we can see that actually we can choose the edges 3C and actually the edge of 4E here. And actually, this is giving us a matching that is composed of 1A, 2B, 3C, and 4E. So actually, another very quick discussion along this is that it is not very hard to see that there is no matching that actually has cardinality 5. So why is this the case? A very quick argument is that if you look at the 2 and 5 here, I mean, 2 and 5, they actually are both only adjacent. They are both only adjacent to the vertex B here. But actually, for the stable matching, you can only choose at most one edge for the B here. So it's just that, I mean, from the left-hand side, we clearly see that, I mean, both 2 and 5, they cannot be simultaneously selected. So just, I mean, look at B. Basically, just look at the left-hand side, we clearly know that there is no measure that can reach a cardinality 5 here. So let's actually write this down. We chosen one same matching. So basically, that concludes that for this example, well, we are pretty sure that the maximum cardinality matching has a value of 4 here. So is there any question about the definition of the bipartite matching in this example? Okay, so if there is no question, I guess let's think about how we want to solve this problem. So I guess what was just discussed just now, that basically maybe want to look at the field vertices. I mean, look at the corresponding structures. This is still a little bit quite special. I mean, just imagine that, I mean, here, I mean, for this matching, we can clearly see that there is no match has cardinality 5. But if there are more edges, for instance, from 2 and 5, there are actually some instances where there is no further maximum matching. But it's then going to be much harder to actually point out this. So in general, maybe we want to have like some sort of general methodology to solve such kind of maximum matching problem. And basically, the thing that we are actually going to do here is that we are going to find a reduction to the max flow. So basically, to do this, we actually see that we have like a max flow formulation for the problem. Okay, so for the max flow formulation of the maximum matching problem, that actually we are going to do is that we basically need to make this somehow like a max flow problem. So there are some construction that we are going to give here. So because the maximum flow problem actually are going to work on a directed. So basically we say that we have basically want to create a directed. Let's say this is a G prime with the vertex set to be a V prime and the X set to be a E prime. So the vertex set that we are going to consider, this V prime, is actually going to be a union of the L and R and two newly added vertices S and T here. So because at the beginning we don't have like S and T here, we basically need to create them, and then we need to figure out what is the construction that we actually want to have here. So this is the vertex set, and the next thing that is very important is that we need to figure out the edge set. So the edge set that actually we are going to have is actually we are going to do this. So basically we direct all edges. I mean, currently already having the original graph, I mean, basically between L and R. So basically we direct all the edges from L to R, from left to right, and assign a unit capacity. A unit capacity is just like one capacity. So this is the thing that we are going to do with original edges. But then we actually added some edges. Basically, we added this newly added source S and the thing T here. We also need to add some new edges. So this is actually going to be done accordingly. So actually, we are going to add a source S and a unit capacity edges from S to each node in L. And the third thing that we are going to do is that we are going to add a sink. We're going to add a sink T and a unit capacity. This time from each node. each node in R. Okay, so let's see what is actually happening here. So let's continue to use this as an example. Okay, so this is a original a bipartite matching problem. So basically for the max flow formulation, we are going to have this graph. So basically at the beginning, we just copy this, but actually we have a S. At the right-hand side, we have a T. Sorry, in S in the left-hand side and a T in the right-hand side. So basically, we add all these directed edges from S to all the vertices in L. And on the other hand, for the T part, we are going to have edges from each node in R to T. Basically something like this. And furthermore, I think basically for the edges in the original graph, we are going to direct all the edges from L to R. So that is basically going to give us something like this. And I guess basically we have been mentioning that the capacity of all the edges, I mean the edges from S to L, the edges from R to T, and also on all the edges in the original graph from L to R. Actually, all of them have weight 1 here. And in the middle, they all have weight 1, so I don't have to write all of them here. Okay, so this is basically the construction that we actually have here. So I mean, as long as we have a rational bipartite matching problem, so basically we have this graph here. We have the L part and the R part represents two parts of the bipartite respectively. And then we construct S and T here, and basically we then construct such kind of a directed graph from S to L, and then from L to R for all the original, for all the edges in the original graph, we just directed their direction from L to R, and finally from R to from R to T here. So basically, we have this kind of construction. And the thing that we are going to show here, a main theorem, because after all, we have been talking about the max flow algorithm. So the very important thing is that we need to solve this problem, of course, correctly. So basically, we want to show that the max cardinality matching in original graph G here actually equals to the value of the max flow in this new graph G prime. So this is basically a theorem that we are actually going to prove here in a minute. So before we do that, is there any question about this network flow formulation? So basically how we transit from a bipartite matching problem to a max flow. Is there any question for this definition? Okay, so if there is no question, let's actually get into the proof here. So basically the proof actually has two parts. I mean, because basically we need to prove that the max cardinality matching in G here equals to the value of the max flow in G prime. So there are basically two sides. So we are actually basically to show that this value is actually both larger than or equal to left-hand side is actually both larger than or equal to the right-hand side. Actually, the left-hand side is actually smaller than or equal to the right-hand side. So in that case, we know that actually they must be equal. So let's actually show the first, maybe show the smaller than or equal to case. So in this case, I mean, basically we assume that we have a value of the maximum cardinality match in G here, and basically we need to then consider what is the value of the max flow in the G prime here. So let's say that we are given the matching, given a max matching. M, let's say of cardinality K. So basically we consider the flow F that actually sends one unit along each K paths. So basically we know that such kind of F, it is actually is a flow. because it is actually a maximum matching here. So maximum matching here is, for instance, maybe let's look at this graph. So a key point of the matching is that, I mean, different vertices, they actually don't talk to each other. And actually for an edge here, I mean, each edge actually is only adjacent to at most one vertex here. So the key point is that as long as we have a max matching, I mean, say that has a cardinality k here, we can then consider a flow that actually sends one unit along each of these k paths here. So basically, this is actually going to give us that the f is actually a flow, and actually the flow has cardinality. I mean, I should not say probably not has cardinality, but actually the flow has value k here. So this is basically saying that just the value of the max flow in G here, sorry, in G prime here is actually at least. So what is the intuition here? So maybe let's actually further make some a discussion here about this. So we know that this example, is actually a maximum matching in this Bipartite matching problem. So basically, we know that as long as we have a matching like this, so basically we know that in this graph, we actually get promise that we have a flow with value 4 here. So the max flow has corresponding value at least 4 here. So why is that the case? This is just the case because it suffices that we can consider this graph. We consider this graph. So basically we have a S here and actually we have a T here. So we consider this. So we consider that basically we have we use the capacity 1 here. And actually for the other edge, I mean, we just don't use this. So basically, let me also actually finish the right-hand side. So basically, for all of the red edges here, so basically we have a matching in the middle here. I mean, 1A, 2B, 3C, and 4E here. So basically for this edge, we actually are going to utilize the weight. Oh, excuse me. We're going to use the unit capacity here, the unit capacity here, and actually the unit capacity. And actually we use the unit capacity here, unit capacity here, and actually the unit capacity here. So this clearly gives us that basically, I mean, for all these paths, I mean, it definitely satisfies the definition of the max flow problem in this graph. And actually, we are pretty sure, I mean, this gives us a flow of value of 4 here, which is actually suggesting that the max flow is only going to have a value at least 4 here. Okay, any question about this part, smaller than or equal to? Okay. So after proving the smaller than or equal to part, of course, so next thing that we are going to do is the larger than or equal to part. So that is basically saying we need to prove that, I mean, the value of the max cardinality matching in G here is actually larger than or equal to the value of the max flow in G prime here. So in some sense, I mean, you can imagine that this is basically another type of reduction here. That basically we are going to consider like a flow. When you consider a max flow in G prime here, basically we are going to see that as long as we have a max flow in G prime here, how this is actually going to give a max cardinality matching here. So let's show the proof here. So the first thing is that let's consider F to be a max flow. Let F be a max flow in G prime of value K. So we have shown the integrality theorem. That actually this K must be an integer. And actually we can assume that the value, I mean, the value of this basically on each of the edges in this max flow here is actually a 0 or 1 here. So because basically this is because in this graph, I mean, all the edges, they have integer capacity. So the integrality theorem is actually going to work. I mean, if you have a capacity on each edge to be 1 here, it is an integer. The only choice is that basically the value, I mean, the f value here, I mean, on each edge should only be at most 0 and 1. And this, the only two choices that we can actually have. So let's then consider M to be the set of edges. From L to R with Fe equal to 1. So basically, we consider all such kind of edges here. So what is actually happening here? So let's actually take a look at this. So suppose that this is actually a max flow that we found in this graph. So basically, I mean, after running the focus algorithm on this graph P prime, we figure out, oh, okay, so this is the a max flow that we can actually achieve here. And actually this max flow has a value of 4 here. So basically, let's actually, leave a few further lines to finish the proof. But the intuition is that as long as we have a max flow like this, so basically we run the focus algorithm on this graph. So basically, we can conclude that in general, we can just conclude that we consider the set M to be the set of edges from L to R with Fe equals to 1 here. So basically, after having that, it suffices that let's say that we copy this here. So here we just consider M here to be all the set of edges from L to R with Fe equals to 1. We are actually now safe to discard S and a T here. And also, it is we can feel free to discard the direction of the edges. So we just consider all the edges from L to R with the corresponding Fe equals to 1. And then basically this here, I mean, basically you look at all the right edges here. I mean, okay, so we get a matching. I mean, 1A, 2B, 3C, 4E here. And actually this is indeed a matching. So this is the intuition that behind this, but for the completeness here, let's finish the proof. So basically, we just consider this M here, and actually we are going to prove that this is indeed. This is actually very difficult to do because we just say that due to capacity constraints, edges between S and L. And also on the other hand, between R and T. So each node in L and R distributes at most one edge. And actually, this just a promise that M is actually a match. Okay, so now we know that M is actually a matching, and actually we are going to prove the larger than or equal to side, that basically the maximum cardinality matching is larger than or equal to the value of the max flow. So this is actually very simple to see because actually the cardinality of M just equals to the cut between L union S, and actually let me write a small s here, and R union with, I guess I should probably use the set notation. S. R union with T. And actually, this is a cut, and a cut is actually larger than the value of mean cut. But we all know that the value of the mean cut equals to the value of the max flow, which equal to K in this case. So basically, we finished the proof that the cardinality of M is indeed at least larger than or equal to K. And basically, looking at both sides, we actually finished the proof. Okay, any questions about the bipartite matching problem? Okay, so if there is no question, let's take a break and then come back to our discussion about applications of the network flow algorithms.